じゃあ続きまして、同じく JAXA ベンチャーのパッチドコニックスさんより、ティアゴさんによって、Power-Free Propulsion System for Microsatellites with Correction Strategy ということでご講演いただきます。ティアゴさん、音声聞こえますでしょうか？
Hi, good afternoon, everyone. Can you see my screen?
Okay, please go ahead.
Okay, so this is Tiago from Patchedconics. Today I'm going to be presenting about two topics, which are our power-free propulsion system for microsatellites and also our correction strategy. But I'll start in the opposite direction. So first of all, very quickly and briefly, what is an orbit? An orbit, an Earth orbit, is an interaction between Earth and another body with a way smaller mass. And this caused the object to fly and to describe an elliptical trajectory. And one of the cases of an ellipse is a circle, which is an ellipse with an eccentricity of 0. Most satellites are launched, especially small satellites, into low Earth orbit, which go from 400 to 2,000 kilometers of altitude. And at those altitudes, the spacecraft will fly through atmosphere. Even at those altitudes, we still have atmosphere. And because of this, the spacecraft will suffer from decay. So slowly, the spacecraft will lose altitude. Also another, because the Earth is oblate, there are some effects of perturbations on orbits. So even if you launch a spacecraft in a circular orbit, eventually it will wobble and become eccentric and then go back to a circle. So here we can see elliptical orbits and circular orbits. For an elliptical orbit, there is a moment in which the spacecraft flies closer to the Earth, which is the perigee. On the perigee, the velocity is larger, and also the atmosphere will be denser, meaning that the spacecraft will suffer from stronger drag. So it will decay faster if it's on an elliptical orbit, comparing to the same size orbit being circular. So it is interesting if we could have circular orbit. But as I said, even if you launched it into a circular orbit, the spacecraft will eventually, the trajectory will eventually wobble and become elliptical. So there are several ways to correct a trajectory. So once it starts decaying, you can, I will present two here. You can apply an impulsive delta V at the apoapsis, for example, and you will increase the periapsis. And with that, you will increase the orbit size. So you will extend the life of the mission by a few, I don't know, years, for example. Another option is applying continuous delta V during one orbit. This way, you will basically not affect orbital elements. The orbit will keep its shape. So, but it is interesting for us to reach, it is possible actually to reach an orbit that has eccentricity, but the eccentricity is constant. So here, for example, we show the results of one simulation. So we applied an impulsive delta V at the apoapsis of an orbit, and we were able to, so here you have on the right-hand side, the eccentricity as a function of the time graph. So you see that after performing the maneuver, so in blue, you can see that the eccentricity will become constant. So in this case, there is no wobbling, and after performing this maneuver, we were able to reduce the decay by 6% when comparing to a correction applied throughout one orbit. So constant delta V throughout one orbit. So now I'm going to talk about the thrusters, so our propulsion units. So at Patchedconics, we are working with cold gas thrusters, which are very common for space use, and they have very simple operation. One famous use of the cold gas thruster was, for example, on the Man Maneuvering Unit, MMU, used by astronauts to fly without any cord connecting them to the ship. So it works working principle is very easy. You have a tube with a pressurized gas. Of course, before this tube, you have a valve to control the gas input. And on the end of this tube, you have a throat where the gas and the flow will be choked. In the choking point, the flow will be supersonic, and then it will expand on an exit cone, and we can generate thrust. The problem with the cold gas thrusting is that usually require high pressure gas to be stored. But also we can use liquidized propellant with low vapor pressure. In this case, we don't necessarily need a high pressure storage tank in order to keep this propellant. But because it's in a liquid form, we require gas generating function on our propulsion system. And one way to generate gas that we can imagine is by providing heat, and we transform liquid into gas. But interestingly, depending on the fuel that we use, so it's the case for our product, we can provide this heat passively. So we can use of the heat of the spacecraft, so the heat that comes from the sun, or the heat that comes from the electronic components of the spacecraft. So we can heat the propulsion, we can generate gas by passively heating. And also we can use isentropic pressure reduction. So once in this image here, we have the pressure enthalpy graph. And we can see here a constant temperature line. So for example, if we have the spacecraft at a certain temperature, after some time absorbing heat from the spacecraft, the propulsion system will reach this point. So we can reduce the pressure of this system isentropically using our technology, and generating a safe to use gas with no risk of condensation, because we don't want liquid flowing through the pipes and through the throat. So isentropic pressure reducer is the technology that we are currently using, and it's also present on the ALEX engine that was shipped into the ALE-2 spacecraft. This spacecraft is currently operational, and it's able to generate gas with no active power, so passively heating, as I mentioned on the previous slide. The only power-consuming components are the PCBs with the sensors and the valves that are required to operate this propulsion system. So as a conclusion, here I presented our low-cost propulsion system. This is way cheaper than conventional propulsion units that consumes very low power, which is very good for small satellites that don't have a lot of resources. And we are able to extend the life of small satellites into a low Earth orbit by giving them the possibility to propel themselves. And also here we presented a correction strategy, and we can improve the performance of our propulsion. Thank you very much.
はい、ティアゴさんありがとうございました。